we have previously discussed some circuit manipulations to expose the relationship between the different converters and to derive some new ones. There's another way to do this. We can actually derive all possible converters that have a given set of constraints, such as having, say, 2 switching intervals and 1 inductor. Let's not derive all the possible converters. It turns out there are an infinite number of them, and they do some pretty interesting and diverse things. But let's briefly summarize some of the basic results. So what's shown here is, I think, the most rudimentary class of converters, where we have one inductor that is switched between the input source VG and the output load V in 2 different ways. One way during interval 1 and another way during interval 2. Now there's only a limited number of possible ways to connect an inductor between 2 voltages, and pick one for the first interval and one for the second, and we can write down all the possible ways to do that and see what converters occur. And the answer is right here. There are 8 converters that are interesting, in addition to a few degenerate or redundant cases that don't add anything new. And we can group these converters actually into 3 different groups. The first group are converters that we'd call DC-DC converters. Namely, if you have a positive input voltage and the output voltage is always of the same polarity regardless of the duty cycle. There's also 2 converters where when you vary the duty cycle from 0 to 1, the output voltage changes polarity in such a way that these are useful as DC to AC type inverters. And then the last 2 are the inversion of the inverters. So they're more suitable for AC to DC applications or rectifiers. So here they are. The first 2 are the buck and the boost, which we already know about. The next 2 we've also discussed. We have the buck boost and the non-inverting buck boost. So these are the 4 converters in this class. They're all you can make with a single inductor and 2 intervals that are DC-DC type converters. Okay, converters 5 and 6 are ones that you might say are suitable as inverters. And we've already discussed the H-bridge in the last lecture. This is converter number 5. Converter number 6 is pretty strange one. It was invented, actually, the transformer isolated version of this was invented at the Watkins Johnson company, and we call this the Watkins Johnson converter. And it has this conversion ratio 2D minus 1 divided by D. It looks like this. But it passes through 0 at D and a half, and it can make either positive or negative output voltages, although the M of D function is a nonlinear one. And then the last 2 in this class are the inverse of numbers 5 and 6. So converter number 7 is what you get if you swap the source and the load of the H-bridge, and this one is sometimes called the current fed bridge. So its conversion ratio is 1 over 2D minus 1, and at D and a half, the ideal conversion ratio goes to infinity. So here's a plot of its conversion ratio. This is a pretty strange conversion ratio, but in fact, if the input is a sinusoid and you want the output to be DC, this is the conversion ratio that you need to perform this rectification function. So when the sinusoid at the input passes through 0, and the output voltage is non-zero, then the ratio or the conversion ratio goes to infinity. But in fact, we're not making infinite output voltage, we're just holding up the output voltage when the input is going through 0. So if you vary the duty cycle sinusoidally about a half, then you can convert an AC input voltage to a DC output. And then the last one is what we get with the inversion of source and load with the Watkins Johnson converter, and its conversion ratio is the inverse, which also goes to infinity at D and a half. So those are all the converters that are possible if you only have one inductor and you have two switching intervals. Well, we can think of other classes of converters, and the next most logical class might be the class of two inductor type converters. So we have two inductors and we switch them one way between the source and the load for the first interval and a different way for the second interval. There are many more than 8 members of this class of converters, and they can do some pretty interesting different things. Here's just a couple of them. The Chook converter, we've previously mentioned and derived this by cascade of a boost followed by a buck converter. It's an interesting buck boost type converter. It's also inverting. The SEPIC is another converter in this class. The transformer isolated version of the SEPIC was invented in Bell Labs in the 1970s, and they call it a single-ended primary inductance converter whose initials are SEPIC. It turns out to be a non-inverting busbook converter, and it's interesting, actually finds quite a few applications. It's interesting for one because its transistor has its source grounded, and you realize the switches with the transistor and diode like this. So it's easy to drive this transistor with a low side driver and get this non-inverting buck boost type characteristic. Here's another converter, is the inverse of the SEPIC. It's also a non-inverting buck boost type converter. Some people call this a zeta converter. Then there's a lot of very different converters. Some of them have what we call the quadratic conversion ratio that are functions of the duty cycle squared. Here's another one of those that was in an earlier homework assignment that has a conversion ratio equal to d squared. And it's interesting that you can get such a conversion ratio in a converter that has 3 diodes and only 1 transistor. We can get quadratic conversion ratios that have other functions such as buck boost squared or other types of conversion ratios by some of the members of this class. So there are some very interesting and exotic conversion ratios that are possible. In general, if you have an arbitrary number of inductors and switches we can build there are infinite number of converters that are possible, and in this universe of converters there are many different and unusual functions of duty cycle, and some of these can have practical applications.